So who are we missing here? Who's the third student that comes here? Don't know. Eventually I'll get to know people's names. I'm terrible with names, but let's see. Is it Amber? Or is it, no, because Jacob's the one who watches the videos. What are your names again one more time?
Bryson.
Bryson and
Ryder.
Ryan and Bryson, okay. That's going to be difficult. I'm going to mix you guys up all the time. So where are you guys from?
North Platte.
Also North Platte? Kind of. Where are you from? Wellfleet? Okay. Good deal. Excellent. Hello, you must be Amber.
Yes, I am.
Nice to meet you.
Nice to meet you.
All right. Is it awkward to sit there and watch the screen? Are you okay with that?
It's fine, yeah.
We can move tables around if we need to. Still waiting for our student in Imperial to come up. She hasn't done so. Don't know why. Rascaland Days Parade. Still don't have anybody connected with us here. All right, well, we'll wait, see what happens. So, where are you from, Amber?
Here in town.
Here in North Platte. So, are all three of you? Oh, here we go. Hello, how are you? Okay, Brittany, how are you?
Good.
You can hear us?
Yes.
Excellent. Well, it's nice to finally meet you all, mostly in person. We are going to record this class, and it should go a lot more smoothly now that we're kind of doing this from the school. I want to get to know you just a little bit before we get started. I was just talking with our students here in North Platte. We have one person from Wellfleet, two from North Platte. Are all of you just finishing high school or coming back from college or what?
I'm coming back from college.
This
So-
is my first year of college.
First year of college, okay. And what are you all studying? Anything in particular?
I'm pretty bad.
Pre-vet?
Yep.
How about you?
Meat science.
What is it?
Meat science.
Meat science? Okay.
I'm going into radiology.
Radiology. Okay. I had several students that have been pre-vet and in radiology, but never had them in meat science. That's new. Although I knew a professor who was into that, so out here at the University Farm here. So that's actually a great place to do an internship. They're always looking for students out there if they're interested. But so, Brittany, what are you studying, and where are you from?
From Imperial.
Okay.
And, I'm doing the stuff for radiology.
So another radiologist. Excellent. Well, the goofy thing is for radiology is they have you take this class for radiology, but unfortunately you're not going to learn much about the stuff that you're going to use in radiology in this class. That's the second semester of this class. I don't know if you have to take 2 semesters or just 1, but most schools only require you to take 1, which I find strange. They should have you take the second semester, but you can't take the second semester without the first semester. We actually just finished the second semester of this class in the spring semester, and then we went and took a tour of the nuclear medicine facility at the hospital, which is always fun. If you ever want to do something like that, that's worthwhile in radiology. It's best to go to a big hospital where they have the MRI machines and the PET machines and all of that, and then they actually do where they actually do the cancer seeding and all that, because that's the most interesting stuff, I think. But I have a few friends and some students that work there, so it's good stuff, good times. Well, I am Jared Daly, and I am a physicist by education, and by experience, I'm more of an engineer. I have worked as an engineer for a company called Moxtech, which Moxtech was a business that was literally created to support the Mars rover program. And so we were designing X-ray devices to put on the Mars rovers. We got a couple of our devices up on Mars, so that's kind of fun. But then I've also actually started school again, so I'm actually a UNL PhD student working on a degree in biological systems engineering, which pretty much means I'm learning and doing research on irrigation in farms. So that's what I'm doing. Irrigation science, irrigation engineering is my new digs. But I just started, and it'll take me probably 7 years to get done because I only take one class a semester. And I have a lot of research to do. But anyway, let's go ahead and ask. There's a couple of questions. I'm trying to figure out what am I doing here. How do I switch to? Oh, here we go. Share. I'm going to share my desktop so that you can see what we're doing here. But I know that we have. Some people that are worried about the due date for chapter 3, which is today. Is that what it's due? And some people are still working on chapter 2, from what I've heard. So let me change that really quick. I have to make sure that I turn off the screen when I enter these things, because don't want everybody to see everybody else's grades. But let's take a look. Oh, I can do this without any problem. So on the calendar, we have homework 2 was due Monday, but that's something that we need to change because not everybody finished that, from what I understand. So chapter 2, we still have a few people that need some time on that. If I opened up chapter 2 until tonight, would that be sufficient? If we answered some questions today, you think? Does anybody have any feedback on that idea? Anybody wants to say differently? Tonight, okay, for chapter 2? I'm going to do it then. And then chapter 3, I'll go ahead and kick down the road until maybe, let's say, Friday. We don't want to get too piled up in this class. We want to eventually start to be able to maybe do a couple of chapters a week if we can. It's really going to be necessary to finish the class, but we'll see how we do. So right now I've got chapter 2 due today at 11 p.m., chapter 3 due Friday at 11 p.m., and then I've put chapter 4 and 5 next Tuesday and Thursday for now. Actually, I'll put them next Wednesday and Friday for now, and we'll see how that goes. We'll see how much we can get done today and see where we're standing at the beginning of next week. This summer class is very much kind of a flowing thing because summer's a little bit crazy and because we're trying to fit so much stuff into a short time. So it will be very much a malleable schedule. If we have to shorten things up a little bit and rush through things, sometimes that happens. But we'll hopefully try to get you everything that you can find useful for your future careers. So the first question I'm going to ask about homework is, does anybody have any homework questions for chapter 2? Would anyone like me to explain, point you in the right direction for anything in chapter 2? Turn this back on. Brittany, you have any questions there from imperial.
Yeah, so I'm trying to figure out which one it was. Hmm. I think it was like problem 17, maybe? I don't know. I just had trouble with the formula.
So number 13 in chapter 2 was this one that has this picture of the plane and the hot air balloon and the runner. Is that the one?
Not that one. Not that one. That one, I think.
Okay.
Yeah.
So in all of these problems that involve kinematics, and kinematics is something that we will use quite a bit for most of the semester. So it's kind of, this is why we hammer it so hard here. I don't know how many questions I gave you, but probably too many. 23, that's not too bad, but it's a lot. And we're always looking to find a kinematic equation that we can use or manipulate and then use, and then get what we're looking for. So remember also that in our kinematic equations, velocity F or V final is in the book it shows us just V instead of V final. They remember that they changed that at the beginning of chapter 2 from V final to just V. And our initial velocity is always V with the 0 underneath it, or V naught. It's often called V0 or V naught. And so we're looking for an equation that covers these things. We have a car that accelerates from rest, rate of 3 meters per second squared for 6 seconds. So they've told us the acceleration rate. They've told us the acceleration. They've told us the time. And we want to find the final velocity. We look for that. And then the second one is to find the distance using all the information that we have. So first things first, let's go open our book. And look in chapter 2 for this stuff. So we're looking at, we want to look where we have acceleration, constant acceleration in one dimension. That would probably be good because this is a constant acceleration issue. Almost all of your problems will be constant acceleration problems unless they specifically say that they're not. So here are some equations. We have the definition of velocity, and then we kind of simplify that by, or I guess spell it out a little bit, and then we solve it. And we also have an average velocity in this box. If we go down further through this section, we have a final velocity equation. Now this one looks promising right here for us. That's a final velocity. Remember that final velocity is the v without anything, and then the v naught is the initial velocity. A is acceleration, t is time. Then if we go down to the very end here, they give us a box. Here they give us another equation, the v squared one. But at the very end, they give us all of them. This is a great place to remember, or something, make a copy of it, or something like this. This is a good thing to kind of have with you all the time. And in fact, I actually have, if you're interested, I have some of these. And I will send you one of these, Brittany, because I'm going to send you your labs hopefully today or tomorrow. And I'll send you one of these cheat sheets with it. So this is a quick study sheet for physics. See if I can get 3 of them here. There you go, 4 of them, that's good enough. Then you're welcome to use this for your homework and your exams as well. You can, and on the exams are open book, so it's a good idea to kind of be familiar with your book. But on this chart here, it's kind of this color-coded thing. The very first page here that says physics at the top, vectors and coordinate systems. This is kind of useful, especially just to remember some of the trigonometry things down here on the left for two-dimensional stuff that we will use. The rest of it is not really all that applicable to this class, but this stuff over here, you could even look at the vector algebra stuff. Is kind of useful sometimes too. It might get a little confusing because there's some things in here that you do not use, and the notation is a little bit different, but it shouldn't be too bad. But on the last page on the inside, not on the back, but on the last page on the inside, we have particle kinematics on the left here, this pink section, and that is definitely useful. We will definitely be using that. So you have all these equations here that are particle kinematic equations at the top. So, and they do have some equations in here that involve calculus, so just ignore those, the dx, dt, the dv, dt, those things. Just ignore those and look at the equations below. Those are the kinematic equations. They call it two-dimensional rectilinear motion. Anyway, it's just it's a useful little thing. If you want to use it, you can, and I will send you one, Brittany. I often think it's best to just know where things are in the book, and you're more than welcome to print off any parts of the book that you want. My rules are in my class is that there are no notes allowed on tests, but you can use this little cheat sheet and you can use your book. But if you have a printed copy of the book and you're taking notes in it, or if you print off the parts of the book and take notes on those, that is perfectly okay with me, as long as it's not a sheet of just plain notes. It must be with the book. And the reason that I'd say that is because I think that's actually a helpful study habit, to make notes in a textbook. Whereas just writing things on a page is not a helpful study habit. That's usually just cramming things on a page and trying to get as much information down that you can look up during a test as possible, right? It's not really helping you learn. But if you're writing within the text in the places where it makes sense to write things down, you will learn things, you will remember things better. So that's my policy for that. Anyway, so these are the kinematic equations. These 5 equations are considered the kinematic equations, but there are also the equations that define things like change in position, the definition of velocity, definition of acceleration. All of those things are actually in here somewhere. Like, for example, if you rearrange this one, you'll get the definition of acceleration. If you rearrange this one, you'll get the definition of velocity. And if you recombine these things, you can get everything out of this. In fact, you only need 3 of these equations, and you can get all the rest of them from recombining them. But what we're trying to do here is find an equation that has the things that we know and has the things that we want to know and nothing else, right? And I think this one here qualifies for that first part of number 15 or whatever it was. 15, yeah. So here we want to know the final velocity, we know the acceleration, and we know the time. And we know the initial velocity is 0 because it accelerates from rest. And then we know, if we want to know how far the car has traveled after 6 seconds, we go back and we say, well, which one of these is going to tell me distance if I know all of this stuff, initial velocity, final velocity, acceleration, and time? Well, this one would do it, right? The final position would be the distance if the initial position is 0. So if we start at x naught equals 0, then our final position will tell us our distance. Initial velocity here, time 1/2 acceleration times time squared, and we can calculate that one. So you use this one in part A and this one in part B, or first part, second part, since they're not labeled A and B. And I would highly recommend that you make a drawing, write things down. It's extremely important to try to visualize this. These are very simple problems. I guarantee you we will have much more difficult problems to deal with where you will want to write things down. So it's good to get in the habit. And if I was doing this problem, I would make a very simple car. That's a good car. Give it a windshield. Anyway, I would draw a very simple car, And I would say, I would label things like my initial velocity equals 0 because it starts at rest. And then I would say that it's going to go up. Let's just say it's going to go this way, and I'm going to label this arrow as a vector for acceleration. I'm going to call this my acceleration equals whatever it was. I don't remember what it was, meters per second squared. I'm going to write that down, and then I'm going to say my velocity final over here is going to equal what? I don't know. So I'm going to put a question mark, and maybe I draw a little thing here that shows the distance that I've traveled. I'm going to call that x. Distance is actually final position minus initial position, x minus x naught. But in this case, my x naught is equal to 0, so I just get rid of that one because it equals to 0. So this distance here is just x. And so then I can start to write down equations. I start writing down a kinematic equation for distance, for example. Here's a kinematic equation for distance. Final distance equals initial distance plus velocity times time. Well, I look at this equation and I say, well, I don't have the velocity, but I do have the time. I didn't write the time here, but I should. My time was equal to 6 seconds. Sorry for my terrible handwriting with my mouse. But I do have my time, but I don't have my velocity. And I have my initial position, but I don't know my final position. So this equation is not really going to help me. And also, this equation is only for a constant velocity, so it's no good anyway. I need to find one that has acceleration, so I go on to another equation. The other equation that gives me position or distance is this one, x equals x naught plus v naught t, it's initial velocity times time, plus 1/2 at squared. Well, this one will give me what I want, except I'm going to have to know, well, I won't have to know anything. This will give me everything I need. It's really good. So I can solve this with my time and my acceleration. It'll give me my final position if this one is equal to 0 and this is equal to 0. Right? So those two are equal to 0. So drawing the picture, writing down the formulas, labeling all the stuff you know and the stuff you want to know. This one I don't know, so I put a question mark there. Is just it helps to organize the mind. The mind, everybody's mind is extremely visual, unless you're pretty much blind. For the 99% of the population, seeing something is the most important thing to understanding it and to making connections in our brain. And so drawing is very important. And it doesn't really even matter if you've taken a test and the test told you that you're an oral person or whatever, that you hear things. That has nothing to do with it. That just means that you're better at hearing things than some people are. Still, even if you're an oral learner, seeing is your most important tool for learning, unless you're blind. Seeing is still the most important tool for all human beings. We are just extremely visual, and that's just the way it is. So draw it out, write things down, organize it. Leave yourself lots of white space. Don't crowd things on your paper. Make sure that you can get the work done without getting confused. Also, this can help you to see any mistakes you might make later. So I would highly recommend it. All right, how do I get out of this? I don't remember. Let's see, go back here maybe? I can't. Nope, that's not it. I can never remember how to do that. How do I get out of it? Do I just close it? I must just close it. There we go, yeah. Close it. Okay. Okay, so now, any other question? Did that answer your question, Brittany? Was that sufficient, or do you have any other questions concerning that?
Yeah.
Okay.
I think I'm just confused on which equation we use.
Yeah, and again, sometimes they're using d for distance, where in our equation it's x. And that's something, again, you have to get used to in physics and science. Different people use different variables, and it doesn't really matter what they are. You just have to understand what they are and make that connection. That frustrates a lot of students, but it's just life. Can't really help it. If I changed, I could change everything, but then it's not going to prepare you for real life in a scientific world. In a scientific world, nobody uses the same anything. It's just not the way it's done. So you have to get used to it. Very helpful to know how to do that. Any other questions from any other problems from chapter 2? Okay, does anybody have any questions from chapter 3 that we need to address right now?
14.
Number 14 on chapter 3, okay. And I can tell I'm going to dehydrate myself today. Every time I start teaching again after a break, I get super thirsty. Ah, yes.
Maybe it's 15 actually.
15? Okay, yeah, this is a really good one. Okay, before I start this, I'm going to have to get a drink of water. Because my mouth is parched. So I'll be right back. I don't have to look far. So this problem is a really good problem for learning how to do solving a problem formulaically. And there's 6 of these cannons, even though only 4 of them are on the purple. And what we want to do is we want to solve this problem without plugging any numbers in, because we want to solve it once and then plug the numbers in 6 times. So how do we do that? So what are we trying to do? First thing, we read this. So we have cannonballs. They've already drawn pictures for us, which is nice. The cannonballs are being shot straight horizontally at the velocity shown below. If they come out of the cannon at the height shown, rank them from shortest to farthest horizontal distance traveled before hitting the ground. Now, we really haven't done anything like this. The other day, in my recorded lesson, we didn't cover this yet. And so this, let's see, this actually may be better taught if we go back to chapter 3 and finish up part of chapter 3 really quick, which is the projectile motion. So let's go back to projectile motion here in chapter 3, and then we'll come back to that problem in a little bit. So, what is projectile motion? Projectile motion is the type of motion that occurs when an object is given some kind of initial velocity by some initial force. So in this case, we have this person kicking the soccer ball. But once the ball has left the person's foot, there's only one force acting on it, and that is gravity. After the foot is not in contact anymore, it's not applying its force anymore. But the ball already feels the effect of that force. It has this velocity up in this direction. But as gravity starts to pull on it, gravity turns the ball, right? Now, if there is no other force involved, no air resistance, no wind, no, somebody coming in and hitting the ball with something, if there's no other thing going on, then the ball, the force of gravity acting on the ball is only going to do one thing to the ball. It's going to turn it. So its initial velocity, which is pointing upward and to the right here, will eventually be turned and turned and turned, and eventually this velocity will be going, eventually this ball will not be going upward and to the right. It will just peak out here, and then it will be going downward and to the right. However, one thing is quite important to know, and that is, if there is no other force involved, no other friction or anything like that, the horizontal movement will not be affected at all. Okay, now this is something we talked about already. This was the idea with the bullet coming out of the gun, right? The sideways motion or the horizontal motion is not affected by the gravitational motion or the vertical motion, right? So it is the same here. And this gives this trajectory of this ball a particular shape, which is, it turns out to be parabolic because of the mathematical nature of gravity, the way that gravity pulls on things. It ends up giving us this quadratic kind of thing going on. So we get this parabola, this kind of inverted parabola. And in the kinematic equations, we're going to essentially have two sets of equations. We'll have a set of equations in the horizontal direction where the acceleration in the horizontal direction is 0 because after the ball has been kicked, there is no more acceleration, no more happening nothing else happening in the horizontal direction. So the only equation really that is going to, let's see here, there's actually one more. No, that's the only equation. This equation is going to be the only equation that'll be valid in the kinematic equations for the horizontal movement. And essentially what this is you take the horizontal velocity of the ball, or the velocity in x, multiply it by the amount of time that the ball is in the air, and you'll be able to figure out how far it goes horizontally. It's pretty simple. So that's really the only equation we've got for the horizontal movement. In the y direction, or in the vertical direction, all of the kinematic equations will be valid because there is acceleration. So we can use all of them, any of them. And the idea here is to use one of these equations and get something that we'll be able to use in the x. Now, which one of these variables is in both the y equations and the x equation? There's only one variable that's in both. Which is it? What is it? What do we got? We got up here x, x naught, vx, and t. Y naught, v naught y, vy, t, vy, v naught y, g, and t. What's the only thing that's in both of these? T, right? The time doesn't change when you change direction. The time doesn't care what direction you're going. Time just kind of marches on, right? And the time is the same in both of them. If 5 seconds goes by in the y direction, 5 seconds goes by in the x direction. Time is kind of independent of direction, whereas everything else depends on the direction. Y is only an up and down direction. X is a side to side direction. So the idea in these problems where we're doing two-dimensional things like this, in this particular case, the projectile motion, the idea is to use one of these equations, usually in the y direction, to figure out what the time is, and then use that time up here to figure out everything else. Or if they tell you the time, then you can use the time in either one of these to figure out something, and then figure out everything else. Okay? So it can get a little tricky. I'm sorry if I seem like I'm melting in my chair, but I hate sitting in a chair. It's really the only way to do this when you're teaching from a computer. So it's obnoxious. Okay. So let's take a look at this motion really quick. This is like that kicked soccer ball. You give it this initial velocity upward and to the right, and gravity is pulling on it downward. So there's a constant acceleration pulling this ball downward. As it pulls it downward, that upward part of the velocity, that upward velocity component, gets smaller and smaller and smaller until it stops. At the top of the motion, it's not going up anymore. It is stopped. And it starts to go down. It gets pulled down at that point. So it's turned over and starts coming down. It gets faster and faster and faster. At the point where it was kicked, it will be going the same speed downward as it was going upward to start with. And the sideways motion hasn't changed. Notice that this x component of the velocity just stays the same the whole time because there's nothing pushing it side to side. There's only something pulling it down. Now, if it keeps going past the point where you kicked it, it will go faster and faster and faster and faster. And if you disconnect these two motions from each other, you look and see this x component of velocity is just the same. The velocity in this direction just the same the whole way. In fact, if you just kicked a ball with this small component of velocity along the ground, then it would just putt along the ground here, and it would get hit by this one as it comes down, right? And this one was going much faster, but it had longer to go. It had to go all the way up here and go back around this way. So it was going faster the whole time except right here, where it was going the same speed, but it was going faster all the rest of the time as it tried to catch up to this other ball. Now the vertical motion, if you break it away from the total motion of the ball, then you just get this fast ball going up, and then it slows down, stops, then it speeds up in the other direction and goes down, 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 faster and faster and faster, right? And this, of course, is what happens with fireworks, for example. In this problem, we have a fireworks display where a shell shot in the air has an initial speed of 70 meters per second. So that's this green vector arrow here represents 70 meters per second of initial velocity. An angle of 75 degrees above the ground, that's this angle right here. And the fuse is timed to ignite the shell just as it reaches its highest point above the ground. So how are we going to figure out where the highest point is? What do we know about the highest point from these graphs here? What is unique about where it's at its highest point? Is there anything unique about it? This is the highest point right here. This is the highest point right here. What's unique about this highest point? This is the highest point right here too, I guess. Nope, right here. This one doesn't show anything unique. These all have the same blue velocity, right? But what's different about this one and this one at the highest point? It stops. There is no up arrow or down arrow. So in the vertical direction, it has stopped. That means if we want to calculate where the highest point is here, using one of these equations, the velocity in the x or the velocity in the y direction has to equal 0, right? The final velocity in the y direction is 0 when it's at the top. So what we're going to do is we're going to use this equation right here, which tells us the final velocity in the y direction equals the final initial velocity in the the initial velocity in the y direction, and those are both squared, minus 2 times gravity, 9.8 is gravity, and then the difference in height, y final minus y initial. That is the number we're trying to calculate, this difference in height. But we're going to use for our final velocity, 0 right here, and our initial velocity will be whatever they told us it was. Now, they told us it was 70 meters per second, but we only want the y component of that. So we're going to have to break it into an x and y component. So we do that down here using the sine of the angle, 75, times 70 meters per second. So that's our initial velocity. And then we're going to plug that into our equation. Our equation looks like this when we've plugged in 0 for the final y velocity. And then that equals the initial y velocity squared minus 2gy. And then we solve it for y, where it's only y because our y naught was 0. We solve it for y and we get this equation, v squared initial over y, v squared initial y over 2 times g. So we take that 70 times sine of 75 is our v naught squared. We square it and we get 67.6 squared over 2 times g, and it turns out to be 233 meters. Now, why would that be useful? That would be useful because now we know the distance that it travels in the y direction, and we can use that with another kinematic equation to actually solve for the time that it travels in the air. Because there's another kinematic equation that has acceleration and time and velocity or distance. There's 2 of them actually. So you could use that one to find the time, and then when you found the time, you can do stuff in the x dimension as well. You can use that in the x dimension. And that's exactly what they do in part B to figure out how much time it's in the air. This is another kinematic equation that they've rearranged here. And they get the time at 6.9 seconds to go to that 233 meters. For that, that's their final y height. And using this final velocity, initial velocity in the y direction. So the important thing to do in these problems is to just like before, is to find an equation that's going to help you, but then you have to convert things into x and y's, right? So this one we needed to know the y component of the velocity. So we used the sine of 75 right here. Right? We might need to use the x component of velocity in some other part. And then we would use the cosine of 70, cosine of 75 times 70. In fact, they do that right here. After they find the time that it's in the air in part C, they're going to use that time to figure out how far away from them the shell goes in the x direction. So they use that time of 6.9 seconds in x equals velocity of x times t, and they calculate that it goes 125 meters downrange. So this example is a great example of how to work with things that are going through projectile motion, because it gives you all the steps. You're starting off in y, you calculate a height, you calculate a time, and then use that time in the x dimension, solve for an x distance, and so on and so forth. Now it's kind of interesting because you can solve this equation right here that we solved to get the height is pretty general. It's a pretty general equation. And so down here, they actually just write it down. If you have a projectile without any kind of friction going on, and you want to know the maximum height of that projectile, then all you got to do is take the y portion of the velocity, or the y component of the velocity, and square it, divide by 2g, and you'll get the maximum height of that projectile. And that can be very useful in many situations. So not a bad formula to remember and highlight or whatever. So here they do another example with a projectile. So instead of it being a firework that explodes at the top of its motion, it's a rock that comes out of a volcano, and it goes up and over the top of its motion, then it comes back down to the original height, but now it's far away from the volcano. But then it falls even further past its original height, down negative 20 meters. But guess what? It doesn't really take anything different to do this problem, because as long as you define your coordinate system and you use that coordinate system throughout the problem, it will understand that 20 meters below where you started, if where you started is 0, is going to be negative 20. It understands that, and you can do the problem. And they do that exactly right here. They're trying to find out the time, and they use this equation here, which is a quadratic, so it gives you a little bit of a challenge. But in their final position, they put negative 20, because it's going to land out there on the plane somewhere. And they calculate the initial position, they use the initial position to be 0. They calculate the initial velocity in y to be 14.3 meters per second, because that is the 25 meters per second times the sine of 35. Gives them the y component of the velocity. Then they multiply that times t minus the acceleration of gravity times 1/2 times t squared. But this ends up being a quadratic equation. You have a t squared in here, you have a t, and you're solving for t. So what you do is you rewrite this into the standard form, 4.9 t squared minus 14.3 t minus 20, by putting everything on one side, right? And then you use the quadratic formula. Remember that? Use the quadratic formula, and you're going to solve for t. It's going to give you two answers. It always does. But you're essentially going to throw out the negative answer, because that one doesn't make sense, right? It doesn't make sense that it's going to land 1.03 seconds before it goes flying out, right? So your time is 3.96 seconds in that case. And then once they found the time, in any one of these problems, once you found the time in these projectile problems, you can go directly to the x part of the problem and say, well, I know now how far it's going to go, because I know the initial velocity, and that initial velocity in the x direction doesn't change. Final velocity for x is the same as the initial velocity. So you multiply that time times the velocity in the x direction. If you have an initial position in the x direction, you add that on, and you get the final position. And so on. So you can do that pretty handily that way. Here they also use this one. In this one, they actually use the time to calculate the final total velocity of the rock, because the x velocity doesn't change in this direction, But the y velocity changes and it stops up here and then it gets faster and faster. And then as it goes past here, it's much faster when it gets down to here. So to find that final velocity in the y direction, they use that time in a velocity equation down here in the y, and they find the final velocity in y, and use the initial velocity in x and the initial velocity in y in the Pythagorean theorem to find the total final velocity, which turns out to be more than the initial velocity. And then to find the angle of that, they use the inverse tangent, which we've also used. It's the y velocity over the x velocity, take the inverse tangent. And that will give you that angle right here. Now I know this is a lot of stuff, a lot of mathematics. If you can't remember your trig, it may be a little bit, tearing your head out a little bit. But don't get frustrated and just sit there and take it, right? If it's frustrating you and you're not understanding what I'm saying, tell me, and we'll go through it in very, very fine detail. Or you can talk to Patrick, or you can watch a video. If you don't want to talk to me, that's fine. But I'm more than willing to stop and make these things clear, but I don't know unless somebody stops me. So if nobody stops me, I just kind of keep going. So any questions at this point as far as this projectile motion type of problem? Okay, now let's go back to the homework and take a look at the homework problem. Or Brittany, did you have any questions at all?
No.
Okay. All right, so now let's go back to our cannonball problem. Here we have our cannonball shot horizontally out, right? We know right away that that horizontal velocity is not going to change. But what is going to change is it's going to gain some vertical velocity as gravity starts to pull it downward. So what we need to do is we need to figure out what kind of effect that's going to have and calculate the distance it's going to go. And the things that we want to keep in our equation without plugging in numbers are the height, or this would be, for example, if we call this where the ball takes off, if we call this height equals 0 or y equals 0, then y final would be the bottom here, and that y final is something we're going to want to leave in the equation because we're going to want to change that every time. And we're going to want to know some kinematic, we're going to want to figure out a kinematic equation that can do this. So what kinematic equation can give us the distance horizontally if we know the distance vertically and we know the velocity horizontally? And, well, there isn't one. We're going to have to use multiple equations to do this. There is one equation that will tell us the horizontal distance if we know the time, but it doesn't tell us the time if we know the vertical distance. So first thing we need to do is find an equation that's going to give us the amount of time the ball will be in the air if we know the vertical distance. And then we'll use that equation to plug into another equation for the time to give us the horizontal distance if we know the time, if that makes any sense. Now there's a shortcut to this problem that's a simplification that helps us to solve the first part, which is how long is the ball going to be in the air? How long is it going to take the ball to drop from the height that it starts at down to the bottom here? What's the simplification? Can you think of it? How could we simplify this problem to calculate how long the ball will be in the air as it's shot out here and falls towards the ground? Remember that example that I gave you where you're shooting the gun? Did I tell you this example? Where you're shooting the gun perfectly horizontally, and what's the other person doing at the same time? Instead of shooting a bullet, they're dropping a bullet, right? That's the simplification. If we just think of dropping the cannonball, because shooting the cannonball and dropping the cannonball is going to have the same effect as how long the cannonball will be in the air, right? It won't make a difference if I shoot it or drop it. It'll still stay in the air at the same amount of time. So if I can calculate how long it's going to be there if I just drop it, how much time it's going to be in the air if I just drop it, then that will give me an equation for the time as a function of the height. So let's go look at our kinematic equations for this. Oh, and at the end of this chapter, at the end of this section, there's a set of kinematic, no, actually I think it's the beginning of the next one. Nope. Beginning of the first section. Okay. So, in this, no, that's not either. Second section. Where's that sound coming from? Must have been from something on that page. Where are my kinematic equations? I don't know. Kinematics, two-dimensional kinematics. There it is. Okay. All right. So here's our set of equations in x, and if we do it in y, where did the y go? So here it is for y. All these for y, and we have just this one for x. So what we're looking for is something that will give us the amount of time if I know that I drop it. So its initial velocity is 0. I know the acceleration. And that's all I know. Can I figure out the time? If I know the initial, no, I also know the height. So I know the distance it's going to fall. I know the initial velocity is 0, and I know the acceleration is g. So is there an equation that can do that? Well, here, I think this is the only one no, that's not the one. This is the only one. This one you have to know the final velocity. This one you have to know, if you know the final position and the initial position, which is the height, right? That's like the difference, that's the height difference. And you know the initial velocity, which we do know, that's 0. And we know the acceleration, which is 9.8. Then we can calculate the time. So again, we're back to our quadratic, but in this case, we get rid of the t term, and so it's not as difficult. So this is the equation we want to solve for time, where y minus y naught is going to be our height. And when we do that, this is what it's going to look like. Wonder if I can copy it off of here and put it on my whiteboard. Let's try it. Probably not. Nope. Okay, so anyway, so the equation looks like this. The final position in the y equals the initial position in the y plus the initial velocity in the y times time plus 1/2 acceleration times time squared. Now they put a negative 1/2 t squared here, and that's fine, but I'm going to do it this way. So the things that we know that the initial velocity is 0 because we're dropping this cannonball from rest, and then we're dropping it downward, right? So its initial velocity is 0, we're not throwing it downward or throwing it upward, we're just dropping it from the rest. So this whole term in here just kind of goes away, just disappears. And y minus y naught, if I subtract y naught from both sides, y minus y naught equals the height. That's the final position minus the initial position of y. So that equals the height, right? And if I do that by both sides, the only thing I have left on the other side is 1/2 at squared. And we know that the a is equal to negative 9.8. It's just a constant. We can throw that in. Meters per second squared times the time squared, right? Now, another thing that's going to confuse people is when we use this equation, we're going to get a negative height, but that's because we're assuming that the table is at 0 and below it is going to be negative, right? So this is going to give us negative height numbers, but that's fine. When it asks for the height in the book, it's not asking for a sign. It's just asking for a number. It doesn't want you to put the negative in there. So we can actually just get rid of that if we want to. We're working on making that more clear when we do these homework problems, but it's going to take us a while because we don't have anybody hired to change those problems in my open math. But anyway, the height equals 1/2 9.8 meters per second squared times time squared. So this equation now we want to solve for time because we're going to use this later. So t squared essentially is going to equal, we're going to multiply by 2 on both sides, so we're going to get 2 times h. Then we're going to divide by g, so that's 9.8. We divide by g, 2h over g. And then if we take the square root of it, we get t equals square root 2h over g. So that's our formula for time for any height of a table, whatever height it is, if you drop a ball from it. Or if you shoot a cannonball from it, right? Either way, that will tell you how long the ball will be in the air before it hits the ground. Now what we need to do is we need to find an equation that's going to tell us how far the ball is going to go if we know its velocity. So here's the distance it's going to go. The distance is going to be the x minus x naught. And we know velocity initial in the x. We know this one. They tell us that in every part of the problem. So we need an equation that's going to give us velocity final in the x direction. And it looks like this. Velocity initial in the x direction times time. Oops, that's not what I want. We want to do distance. Sorry. And that's not right either. It's, I wrote one equation, but I wrote the wrong equation, and I wrote the equation incorrectly. So, let's try it again. There we go. In fact, let's just look it up so we do it just like they do in the book. Here it is. X equals x naught plus vxt. So x equals x naught plus vxt. Well, what is t? We have t. T is right here. So x is actually going to equal x naught. Now x naught is going to be 0, so we can actually just get rid of that. We don't have to keep that in our equation. It's just going to be our velocity in the x direction times our time, but our time is going to be different for each table. Our time is going to be 2 times the height of the table divided by g. Now you can calculate the distance of each one of those balls, regardless of the height of the table and regardless of the velocity of the original ball, right? It will just, you just plug in the 2 numbers and you're good to go. And you can rank them, you can solve for whatever you want. But the moral of this story is not really getting to the end and getting the numbers right. The moral of the story is we've created a formula for a very specific situation. And this is something that all of you will do and make use of in your professions if you go on the professions you've chosen. Because anytime you're in any kind of scientific profession, you're going to be using formulas, and sometimes, oftentimes, you have to create those formulas yourself. And that's what we've done here. Right? We've taken a situation with a set of equations, we've figured out which equations we need to use, we've solved them, we've combined them, we've created a formula. Useful in any science. Okay. No?
I just have a question on 16. What formula do you use?
Well, here we have, we're trying to find velocity, right? We know the acceleration. We know initial velocity, 29.4, right? And we know time. So what you need to do is find an equation that uses initial velocity, acceleration, which is g, negative g, and time, and gives you final velocity. And you'll be able to do that. And then solve for that final velocity.
Okay.
That one's actually easier than the previous one because you're only going to have to use one equation to do that. Now I'm going to give you a little bit of a clue on number 17 here. In number 17 in the book, after one of the examples, in one of the examples, they actually create a formula for this so that you don't actually have to create it yourself. So, there's actually a really fun thing to do at the end of one of these sections. I can't remember which section it is. Oh yeah, here it is. Here is the cannonball projectile motion thing here. Let's do a golf ball. Tank shell. So here you can set the angle, you can choose the angle, and you can choose the initial speed and the mass and the diameter, and you can decide if you want air resistance, and you can fire it. Right, and then you see what happens. So what we want to do is change our target. How do we change where our target is? I don't know. There we go. So that hits the target right on. Fire. Hits the target right on. Score. Now, what do we do if we change this angle? Let's change it to 20 degrees. And fire it. Right. Change it to 10 degrees. You notice at where it fires from, which is on this yellow line, at 10 degrees and at 80 degrees, it crosses the yellow line at exactly the same spot again. So if my target was actually up here, which it is, which I'm going to put it at, and fire it, and it goes right through it. Fire it here. What if I do 30 degrees? Fire it. Goes way out here. So we move it way out here. And we fire it. And we hit it. And then what if I go to 60 degrees? And fire it. Hits it again. And that's actually a consequence, again, of the nature of gravity. It's this, if you fire something at some angle, and then you fire it at the complement of that angle, which is 90 degrees minus that angle, you'll hit the same spot, as long as there's no resistance in the air. And this is used all. Any of you guys play golf? Anybody play golf? No. This is used all the time in golf. In golf, you have these clubs that have different angles, right? And if you can drive the ball just straight ahead, then you use one that has a very steep angle on it, or a very flat angle, a very flat head. It's just a low trajectory. It's not gonna hang up in the wind a lot, and that's great. But if you have to go over something, then you have to change the angle of the head. But sometimes you have to go over something and still go the same distance, right? So you go over something by swinging it harder and having a steeper angle on it. But anyway, just an interesting little thing there. It's kind of fun. We can throw an adult human. Whoa! Or a piano. That's a new option. That's funny. A Buick, we can fire a car. That's all new. That's exciting. Physicists are goofy. All right, this is what physicists do when they're bored. All right, so anyway, now we move on here. The last section of this chapter that we haven't covered is the relative velocity section. And really this is due to usually you have some kind of a moving medium in which a problem happens. For example, a great example of this is the rowboat in a river. If you point a rowboat to the opposite side of a river and you start rowing across the river, and if you've ever done this in any kind of boat, you know this is the case. Or if you've ever swam across a river, swam in the ocean or anything like this, you know this is the case, that you're never going to end up where you point your boat because the river is pushing you downstream, right? So you row and you row and you row and you row. And if you want to get to across the stream, you actually have to point your boat upstream to get to a point directly across stream. So often on rivers, they actually design docks on rivers sometimes to, you take off from this dock and you just go straight across and you end up at one downstream. And it works out fairly nicely. That was especially true of old time docks for like crossings with the ferry crossings and things like that. But if you fly in a plane, this is also true. The wind acts like the river. And the wind can be pointing in any direction. In the case of this airplane, the wind is actually pushing backwards into the left of the plane. So the plane is flying forward. Like this is actually this dotted arrow right here represents the actual direction the plane is pointing and the speed that it's going. The propeller is pushing the plane in this direction at this speed, at this velocity. The velocity of the wind is backwards to the left, and the total velocity of plane plus wind is actually to the left and forward, right? And you have to really be aware of that in a plane because it's not totally obvious while you're flying. A lot of people think that it's just easy flying a plane, just point A to point B, but no, it's not easy because the wind is always blowing and you're always getting pushed around and you can't actually see where you're going to in a plane. Usually the places that you're going in a plane are too far away to see. The advent, with the use of GPS, it's made it a lot easier to fly planes, but still, GPS is not always working for you because the most common thing that people forget are batteries for their GPS, right? Or their phone. They don't charge their battery. They're in a plane for 4 hours and they can't charge their battery, so they're screwed, especially if it's a small plane. But anyway, this becomes quite important in planes to understand this, and in other things. There's lots of different examples of this, but the idea here is that that there's this added component of the velocity that's changes it, and it adds just like other vectors. This one is a head to tail kind of adding to show this total velocity here. Don't be fooled. This is not a right angle. This looks like it might be a right triangle, but it is not. You'd have to actually figure that out. And how would you figure it out? Well, in the case of the plane, in the case of the plane's velocity, you would break up these velocities, this plane velocity and this wind velocity, into components. The plane velocity, since north is considered our y direction, is all in the y direction. The plane is actually pointing north, and so its velocity due to its propeller is all in the y direction. But this wind velocity has an x component and a y component, and you'd have to break that into two components, and then you would come down here like they're doing and add the components of the y and the y components of the wind with the y component of the plane and the x component of the wind with the x component of the plane, and get a total overall components for the added velocities, and then you would create an overall velocity using the Pythagorean theorem and figure out the angle from the inverse tangent as we've done before. And here they actually do this example of the boat on the river. So let's do this problem and show how this is done. The boat is going in the x direction. The river is going in the y direction. The river is going in the x direction. Both positive velocities. We're going to add these two velocities together to make a total velocity. Since one is in the x direction, one's in the y direction, we don't really have to break them down into components. We just need to add them together using the Pythagorean theorem. We get a 1.42 meter per second total velocity. And then we use the inverse tangent y over x to get the angle of 32 degrees. And that's really simple. But what if it's the airplane? In the airplane, we have one of these vectors that's not just in one dimension. It's partially in the x, partially in the y. So the wind velocity we need to break into components, and they do that right here. The velocity of the wind in the x direction is the velocity, let's see, sorry, first of all, they say the total velocity in the x direction is only due to the wind. So the only x movement we have on this plane is because of the wind blowing to the left. The plane is not turned to the left or the right at all. So that's the only thing. So all they're saying here is that the total velocity in the x direction is equal to the wind velocity in the x direction. And then in the y direction, the total velocity in the y direction is equal to the wind velocity plus the plane velocity. So we start off by finding the component of the wind velocity in the x direction. So you take the total component times the total velocity times the cosine of 110. Now the thing that we don't know here is the total velocity of the plane. And they also do not tell us, let's see. They do not tell us the velocity of the wind. They tell us the total velocity. So they tell us this vector. And they tell us this vector, but they don't tell us the wind vector. So we're actually trying to calculate the wind vector. So that's why we're using the total velocity here, because we know that one's 38. So it's 38 meters per second is the total velocity of the plane. If we multiply it by the cosine of 110, the 110 being this angle from here all the way to here to the total velocity, then that's going to give us that's going to tell us the wind velocity in the x direction, because it's the same as the total velocity in the x direction. So once they calculate that at negative 13 meters per second, then we know one component of the wind velocity. Now to find the total velocity of the, to find the wind velocity, okay, hold on a second. I cannot hear you, Brittany.
Okay.
Wait, now I can hear you.
Okay. It's just frozen on that white screen that you wrote on at the beginning.
Okay, let me try to change this. Hold on a second. So you haven't seen the examples. Do you need me to start over?
No, I think I know where you're at. Are you I have the book pulled up.
Yeah, I'm right here on the
Okay.
airplane example.
There we go. I can see it now.
Okay, sorry about that.
No.
So the first part was the y velocity, the x velocity. So essentially what they're saying is that because the only thing that's pushing this sideways is the wind, then the total velocity in the x direction and the total wind velocity in the x direction are the same. And so they use that one to calculate the wind velocity from the total velocity x component. In the y direction, we take the total velocity, which is the 38 meters per second. Let's see. Yeah, the 38 meters per second times the sine of 110. And then they subtract off the 45 meters per second, which is the velocity of the plane here. So they take the total, subtract the plane velocity, and that tells them the wind velocity in the y direction of negative 9.29. And that makes sense because the wind is pushing backwards here, or downwards, in the negative direction of y. So in the end, we have the wind velocity in the x direction, the wind velocity in the y direction. Use the Pythagorean theorem to calculate the total wind velocity, and then again the inverse tangent to calculate the angle of that wind velocity. So that one's a little bit tricky because they're not giving you one of the things that adds together to make the total velocity. You have to solve for that one instead of solving for the total. And that's the essence of the last section of this chapter, is this this addition of two different velocities to create another velocity. And it has a lot of implications in science. This is one of the classic things here is if you're on the top of a mast of a sailing ship and you drop a pair of binoculars, to the person who's dropping them, he just observes them falling straight down the mast. That's what the person on the boat sees. But if you're on the side of the lake or whatever, you actually see the binoculars move in this parabolic path because they have some sideways motion from the sailboat moving to begin with. And when you drop them, you add the sideways motion to the downward motion, and you get this parabolic motion. Similar to dropping something out of a plane. If you drop something out of a plane, the person in the plane observes, like a better example of this that makes a little more sense, I think, to people would be a bomber dropping a bomb from a plane, right? Not the best example as far as keeping the peace, but if you drop a bomb for a plane, the bomber views the bomb just falling straight down. As long as there's very little air resistance, they just see it drop straight down from the plane. But of course, when you're seeing the bomb drop from the plane, you see it drop in this arc. It drops in this parabolic curve. So, but it's all the same stuff. It's all initial velocities in x and in y, and using these kinematic equations to solve for them independently, and then you put them together at the end, and voila. Right? So, let's see, do that. And then I can do, hold on a second. Okay, so according to my records, it looks like almost everybody has started chapter 3 at least. And that's great. It's most everybody has done really quite well on chapter 2, but just a few questions left to mop up. Now, ideally, the thing to do today would be to start chapter 4, but I don't think that that's going to work very well. Since chapter 3, we are just kind of getting started on the homework. But what we can do is we can go through more problems in chapter 3. If you guys have more questions, we can show you how to, give you some pointers and show you how to step through some of these problems. If anybody has any more questions, or we can just pick a few. What do you guys want to do? Any particular? I hate to end class so early. What time is it? It's almost 5, I guess. What time are we done here? 6? So we have another hour or so. I hate to end class so early in the semester when we're trying to really kind of push things. So let's actually go through a couple more problems in the homework really quick and give you guys, so the best thing to do would be to get your homework opened up and start writing things down. I won't take you all the way through the problems, but I will give you some pointers and some ideas on how to get them done. All right, let's see here. Let's try this. Okay. These ones are fairly straightforward, just two-dimensional vector stuff. That's really too easy. So aircraft has an airspeed of 188 kilometers per hour north. So this might be a little confusing if you're not familiar with aircraft terminology, but the airspeed of an aircraft is the speed that it's moving through the air with. So if we go back to the previous example in the book that we did with a plane, this is the chart. This is the no, that's not. Yeah, here it is. Here's the drawing of the plane. The airspeed is the v total. That's this one. That's the ground speed plus the wind speed. So they're telling you what this one is. So it's very similar to the example we just walked through. This problem is very similar to the example. They've told you the airspeed, and they've told you that it's to the north. And they want to know what is the ground speed. Now the ground speed is this one. That's the velocity of the plane. The ground speed is the one that the plane actually would have if there was no wind. So this is VP is actually ground speed. V total is actually airspeed. And then the crosswind is 53 kilometers per hour to the west. So they've told you the wind speed. So in this problem, it's different in that they've told you the total and the wind, and you have to figure out the ground one. But it's essentially the same problem. You're just figuring out the ground one instead of the wind one. Using this, you'll use the same equations and the same ideas as that example. So go back and look at the last example in this section, example 3.7. Right? In this equation right here, instead of solving for the total, you're going to solve for the velocity of the plane, which is the ground speed, right? Or did they want what did they want? They told you the airspeed, and they wanted the ground speed, so you want the velocity of the plane. Yep. So you're going to solve for this one instead, and this one instead. Same problem. Here they just have you rearrange equations. When you're doing this, you can come down here and you can actually push this yellow button, and you can use this. I don't know if I showed you that before, but these will set up your fractions for you and your sub numbers and your all that stuff. But you can also use just normal math. If you just do 7 divided by y, for example, like this, you can get that preview. And if it's a syntax error, don't enter it like that, because it won't give you the right answer. Same here, they're just having you practice rearranging these equations. So here is the problem where you have a baseball thrown from the outfield to home plate. This problem is almost exactly the same problem as the volcano problem. Okay? So this one you can solve by going back to the volcano problem and kind of stepping through that step by step. Instead of a rock being thrown out of a volcano, it's just a baseball thrown by an outfielder. There's a distance in the vertical because the outfielder is standing up and the catcher is lower to the ground, right? So you have a difference to height. Call one of those heights 0, and the difference can be the difference between the two. Or you can just call the ground 0 and use those two heights. That's fine. It will work either way. Excuse me. But remember, in this case, the ball leaves the outfielder's hand at a height. In this case, they're actually giving you the time. They're saying it takes 2.0 seconds for the ball to get from fielder to catcher. In this case, they don't tell you the speed, they tell you the time. So you have to use that in one of those equations to calculate the speed, right? From that, you can calculate, for example, the speed in x, because you know the horizontal velocity doesn't change. So you can calculate it right away, what it is. This one is just one equation, one calculation, and you're done with that part. And then you use the information from this one to get this one with another equation. and then this will involve the tangent equation. So it's a little bit challenging, but it's all the information you need is pretty much in that volcano problem. Very similar to that one. And this one is very similar to the cannonball one that we did, right? But you have to use kinematic equations first to find out how fast the car is going when it leaves the table. Because it's going to start from 0 velocity and it's going to accelerate for 0.63 seconds across the table. And the table is 1.9 meters long. That information will tell you how fast the car is going when it leaves the table. Then you can use the same equation that you used in the cannonball equation to figure out let's see how far are we going to have to change them. Oh, actually, they don't even have you figure out. Oh, here they have you figure out how far it's going to go. So down here, they change it to an angle coming off the. So then it becomes like the volcano again, right? And then it falls to the ground. It's very similar to the volcano problem again. Football punting. This one, they want to know correct vertical velocity vectors, select horizontal velocity vectors, right? Which one changes, horizontal or vertical? Maybe it's easier to say which one doesn't change. Which velocity doesn't change, horizontal or vertical, after you've finished kicking the ball? Horizontal, correct. So those ones don't change. So you have to find the horizontal arrows that don't change. And then the vertical ones do change. But how do they change? You know, do they go up? Or do they go down? Do they go both up and down? At the top, should there be an arrow? Should there not be an arrow? Something to figure out. All things you can pretty much look up in the book. Another soccer ball kicking the problem. In this one, they're just asking some questions. I'll leave those to you. So what's the best angle, do you think, for getting something to go the furthest if there's no resistance? I should probably write that in, that there's no resistance in this problem. Remember the cannonball thing that we were playing with? If you have something that goes the same distance at 80 degrees and 10 degrees, and then the same distance at 70 and 20 degrees, and the same distance at 60 and 30 degrees, where is it going to go the furthest if it's the same for all those complementary angles? Which one's going to be the furthest? Can you guess it just from having kicked a ball or thrown a ball? 45, right? In practice, is it true? If there's air resistance, is that still true? No, you need to be at slightly less than 45, right? You want it to go maybe about 38 degrees, 40 degrees, because you need to overcome that air resistance. But if without air resistance, 45 degrees is the best. Let you guys figure out these ones. Holy mackerel, what did I do? I can't give you 7 attempts on that problem. That's crazy. All right, I think that pretty much covers all the ones. I think we've looked at all of them at this point. So this one actually is kind of a trick question, but shouldn't be too difficult once you figure out the trick question. Same with that one. All right. Remember, you should be aware that physicists love trick questions. So don't try to overthink a question. If it's not making sense to you, if you're looking at it thinking, I don't understand this, and I've got the first two wrong, send me an email, because it may be a tricky question. It may be asking you something much simpler than you imagine. But if there are no more questions, we really don't have anything else to do. If you want to, you can stay and hang out and work on homework, and I will be in my office for the next hour or so. Then you can ask questions directly of me if you'd like. I imagine Patrick's around here somewhere still. I don't know if he is. So anyway, so is Patrick coming before class to work on homework with anybody? Has anybody worked with Patrick on homework? No? Patrick is available as a tutor, and he's a smart kid. But anyway, I have nothing else to do today, so we can be done. Anybody want to stay and work on homework? Completely up to you. Brittany, if you want to work on homework and talk with me for the next hour, you're welcome to, or if you want to be done, you can be done. So
Okay.
I will pack up a bunch of equipment and send that off to the first person going to Imperial, and I will send labs and instructions and this cheat sheet and everything, and then you can just take that to your house, or you can leave it at the Imperial place if you want. It's up to you, but you can take it home if you want and work on them as you please. All right?
Okay.
We are done. Next week we will have a lab again.
Did you record yesterday's class?
What's that?
Did you guys have class yesterday?
We did, and it is on YouTube. It's
Okay.
called Chapter 3. Chapter 3A, I think. Today's will be called Chapter 3B.
Is there a link to that on the My Open Math?
Yeah, if you go in here to the class videos, it'll take you to a YouTube channel. And let's see, chapter, it should be, where is it? Where's chapter? He did play it for you guys, didn't
We watched that, let them watch it.
he? And you found it just from the link I sent you? I will post it. I don't know where it is, but it's here somewhere.
Okay.
I will send it to you. Here, let's see here. Haynes. Where did I do this? What was yesterday? What is today?
I found it.
Oh, you found it. Okay.
Okay, so
Good.
That's it. All right, then.
Okay.
Have a good one.
You too. Thank you.
was the brains behind it. Steve Jobs was the business behind it.
All right, so we're done. Have a good weekend. Enjoy.
You want the cheat from one?
Yeah, if you have your lab sheets, you can drop them off to me here, and I'll take them.